let's have a closer look at this gate resistance and the transistor layout and try to understand why pretty much everybody is drawing the transistors for 1 micrometer, regardless of the technology node. Whether it's 65, 40 nanometer or 28 nanometer, I've always seen 1 micrometer. It's not important. The real question, Rodrigo, is not for which node. The real question is, how do you get to that number? And in FinFET technologies, we'll come to the FinFET technologies. We don't talk about finger widths anymore. We talk about the fins per finger. And there we are clearly limited by the foundry, but we are working on that. Anyhow, how do you know, how do you try to figure out for a certain node? How do you try to figure out what is the best finger width for this technology? Then you need to figure out what are the contributions to the gate resistance. And if you talk about polygate, well, then you need to know, is my technology using polygate or metal gate? Polygate means obviously 90 nanometer, 65 nanometer, 40 nanometer from TSMC. It's a bit different for ST. It's also different for Intel technologies. If you talk about TSMC from 28 nanometer onwards, I think they used metal gate. And then of course we have 16, and then now we have 7 nanometer and so on. But if you use polygate, there is an interesting aspect you need to realize that on top of the polygate electrode, they put a compound of silicon with a metal, and they call that a silicide. And if the silicide is self-aligned, it's called a salicide. But anyhow, so on top of the polygate electrode, there is a highly conductive layer, which is very interesting for digital, because so this layer on top of it has low resistivity, high conductivity. So that means that you have some interconnect resistance. We have the horizontal resistance because, okay, this is the finger width. But in the end, we need to charge and discharge electrons, and this is the silicon dioxide. We need to push back and forth electrons on top of the silicon dioxide to change the electrons in the channel. So there is a contribution of this vertical resistance. And if you think about it, how do I minimize this vertical resistance? The vertical resistance is the resistance when you look down into the electrode from the top of the gate electrode towards the channel. Well, then you would like to have a large finger width and even a large channel length. And so that resistance is actually minimized if you have more cross-section. And that is the reason why we have a trade-off. But let's take it step by step now. First of all, this horizontal resistance over here, obviously the actual value of that resistance, nobody knows. And you can ask TSMC or ST or GF, they will not tell you. But we can assume that this resistance is proportional to the width of a finger and inversely proportional to the channel length. If I make the channel length larger, I will have a lower resistance. That could be an argument to actually make your channel length larger. If you make your channel length larger, you will have a lower FT, but you will have a lower gate resistance, which might be important for noise. So if you're interested in LNAs and you really want to minimize the noise figure, this is something to look into. It also depends on which side do we connect that gate electrode. Because the gate electrode, as I've drawn it here, it's like this. And you have some physical resistance, yes, of course. But we should realize that there is a lot of current flowing. The gate current, I'm not talking about leakage current, I'm talking about signal current here. That gate current is high all the way to the left, but it's equal to 0 all the way here to the right. There is no current flowing anymore. So that means that not all of these resistors have an equal contribution to the gate resistance because the current is not uniform. And the way to solve this would be based on transmission line theory. You can use transmission line theory to solve this equation. Basically, you have a triangle here, and then the center of gravity of a triangle, it has to do something with 1/3. And that's the reason why we see that 1/3 factor here in the equivalent effective gate resistance. So the gate resistance, how it relates to the physical resistance, you have that factor 1/3. Obviously, if we are able to connect our signal on both sides, and that answers the next question in the chat window, and that's what most textbooks will tell you, just connect it on both sides, then you gain 2 times. First of all, you gain because half of the current is on the left side, half of the current is on the right side, and the distance is now divided by 2. So you gain a factor 4. A factor 2 over here, a factor 2 over there, you gain a factor 4. So instead of a factor 1/3, as we see over here, we now have a factor 1/12. And then the obvious conclusion is, let's always connect the gates on both sides. That's possible at lower frequencies. It is possible to do it at higher frequencies, but it's difficult to guarantee at higher frequencies that half of the gate current flows on both sides. Why is that? Maybe I should add a slide here. So suppose this is your transistor, just putting some gate fingers here. There we go. And your signal comes in from here. That's the signal path from left to right. And then most likely, I'll draw that in blue. We have some drain connections here, drain source, and that would be drain again. So this would be our drain connection, and that's the drain. And that's the output. And so, of course, we can just say, hey, let's connect them on both sides. But what I'm drawing here, this is not a connection on both sides because there is no current. Whether I put this connection or not, it's not going to make any difference. I have to somehow find a way that this current is split in effect in 2, and half of the current flows to the left and the other half flows through here. At high frequencies, this means that I'm introducing an additional interconnect here. Now that interconnect, the impedance of this interconnect is going to be significantly large, and there is no way that you can make sure that half of the current flows to both sides of the transistor. In other words, in our designs, most of the time, we do not even connect the gates on both sides because it just increases the uncertainty of the layout. In most of our designs, we just connect it on one side and that's it. At lower frequencies, at RF frequencies, like say 1, maybe up to 5 gigahertz, you can do this. At higher frequencies, it's extremely difficult to guarantee that half of your current flows all the way to the other side. Vertical gate resistance. The vertical gate resistance is the most important one because that is the one that causes an optimum. The vertical gate resistance here, if you look at it, it's this resistance over here. It's proportional to some resistivity of the poly material. Again, a number that nobody knows, and TSMC or GF or ST is not going, they are not going to tell you that number. But what's important for here is that we see that this is inversely proportional to the length of the transistor and the finger width. So that would actually be an argument to make the finger width larger and to make the length larger of the transistor. It would give us lower resistance. It would give us higher fmax. It's a very good point that you make, Theo. It's about the layout of a transistor. I have a slide on covering how we actually do the layout. You're absolutely right. If you connect it on one side, how do you get the signal? How do you get half of the signal on the other side? It's impossible. So actually, it's better to connect on the bottom side, but then you still lose a factor 2. But we'll come to that. If you're interested in the vertical gate resistance and reading more about it, I think this is an interesting paper on the topic. So it shows again the silicide layer on top of the polycrystalline silicon. Remember that this would be the situation for technologies above, let's say, 28 nanometer. After that, we went to metal gate again. Yeah, metal gate, and then there's, but it's still, the trade-off is still there, in my opinion. Another contributor of the gate resistance is the non-quasi-static resistance, which is kind of a more artificial resistance. It kind of models the effect that if we change the charges in the channel, it takes some time. And that time constant is modeled also by a resistance. This is so very often people would also say this is 1/5 times GM. Now, to be honest, we don't really see this as a limitation because that resistance is very often smaller than any other parasitic resistance. So, but putting all these elements together, and we have the horizontal resistance, the vertical resistance, the quasi-static resistance, and then also the interconnector resistance. Obviously, if we have more fingers, then we also have more distance that we need to cover. Whether we connect it on one side or both sides, it doesn't matter. We have more distance to cover, so we will have more interconnect resistance. Putting all that together gives us an optimum. And the total gate resistance, as far as we can simplify it to one single resistor, has an optimum somewhere between I would say 1 micrometer for 40 nanometer CMOS. And that's also the reason why most PDKs would tell you use a transistor or where the high frequency model is optimized and the high frequency layout is optimized for a 1 micrometer finger width. But if you would like to make a large transistor, making a transistor with lots of fingers, and all those fingers would have to be connected. All those fingers would have to be connected in parallel. Then we see that that optimum over here is shifting to somewhat larger finger widths. And I have an example here, and this is an example in 40 nanometer CMOS. And we have seen exactly the same in 16 nanometer. We are just exploring 7 nanometer. So I can't really comment on gate all around at this stage, but I can comment that for planar, we are able to reach the optimum. For FinFET, we are not able to reach the optimum because we would like to have less fins per finger. Gate all around, I don't know yet. But let's look at 40 nanometers, and basically it's the same in 28. And let's look at the small transistor, 80 micrometer. This is a transistor you would use in a VCO or an LNA. And that transistor, if you change the finger width and you look at the gate resistance, you would see a minimum. Well, it's a gentle, it's a very smooth or shallow optimum or minimum around 1 micrometer. But even if you go to 1.5 micrometer, you're still okay. Now, if you do the same exercise for a large transistor, 180 micrometer, meaning a transistor that you would use for a power amplifier, you see that if you would use 1 micrometer, you're over here. So it's better to actually shift to 2 micrometers. And if you also look at the values that you get, here we have a transistor 13 ohms gate resistance. Here we have a transistor which is 10 times larger, but we do not have, I mean, if you divide 13 by 10, because the transistor at the bottom is 10 times larger, I would expect a resistance of 1.3 ohms. Unfortunately, we have a higher resistance of 3.5 ohms. So what's actually happening here? Well, the end result, I can already show it here, is that a small transistor with a finger width of 1 micrometer does get you to the quoted 300 gigahertz fmax from TSMC. That's the number that TSMC or ST or Intel or GF will tell you, or Samsung. But if you draw a layout of an actual transistor that you would like to use in a power amplifier, you already see this. Actually, you first see this. If you would be tempted to use the same 1 micrometer, you divide your fmax by 2. So you pay the same amount of money for the technology. You burn the same amount of power. I'm not changing the biasing. And your fmax is divided by 2. And is there a workaround? The answer is yes. The answer is, well, you need to optimize your layout. And then you can somehow get somewhat higher fmax. Again, the price is the same, the area is the same, the biasing is the same, but at least we have 200 gigahertz fmax instead of 300 gigahertz fmax. A good question on the Francois, on the metal gate over polygate. I have a slide on that. The value of 2 micrometer applies for any technology? No, of course not. This is an exercise we did for 4 nanometer, but I hope that I've given you the tools, so that you can use it for your technology that you're using. Okay? But definitely, if you I'll give an example on that. We made a D-band, a 140 gigahertz power amplifier in 16 nanometer FinFET. If we would use the same approach as we did in 40 nanometer, we would never get good performance. So you really need to look at what is happening with the transistor and how can you optimize the layout. And that is something that a foundry cannot do. That's my experience. TSMC, ST, GF, Intel, you name it, they cannot optimize their P cells for high frequency performance because they don't know how to draw circuits. They don't know how to design circuits. Taking a bit closer look into this, what's happening here with the fmax. So if you look at the very simplified equation of fmax, it had ft over there. Ft does not change because yes, we are changing the layout, but remember, ft mainly depends on the biasing. We are not changing the biasing, so mainly we are looking at this ratio over here. How does the output resistance changes? How does the gate resistance changes? If you make your transistor 10 times larger, you go from 18 micrometer to 180 micrometer, so you make it 10 times larger, then yes, you do see a reduction of RDS by a factor 10. That's good. So this is reduced by a factor 10. I mean, you do not see too many parasitic effects, but that's mainly because the resistor values here are pretty high. So the few ohms that you add from your interconnects doesn't hurt you that much. But if you look at your gate resistance and you go from 18 micrometer to 180 micrometer, and for example, for 1 micrometer finger width, here we are at 15 ohms, and here we are still at 5 ohms. So you do not see that reduction of a factor 10. And so the real problem is the gate resistance. The gate resistance does not reduce sufficiently because of the importance of all these parasitic interconnects. And where are these parasitic interconnects coming from? They are coming from your back end of line. They are coming from your metal stack. So at a certain point, especially if you want to make power amplifiers, the back end of line is more important, and all the parasitics associated with all those metals are more important than the actual performance of your transistor. That's what we see over here. And so we spend an awful lot of time in optimizing the layout of a transistor for minimal resistance. Let me double check if I have the slide here, but no, I don't have. No, it's a pity. I cannot always include all slides. Because we have done an exercise where we connect the gates on both sides or single sides, and at a certain above 60 gigahertz, the difference is marginal whether you connect it on both sides or not. Anyhow, so here we have a layout, a very layout that a very successful layout that you use in many designs, the gate is over here, goes down, and then you have a strip on the left and a strip on the right. Is it double connected? Yes, but it does. The best would actually be to connect it here in the middle, right? Because then you have half on the left and half on the right. We don't do that because we still would try to connect on both sides. It's just a matter of which parasitic resistance you want to minimize. The sources and the bullocks are all tied together. That's good. That gives us a low. If you go look again at the parasitic resistance that you have, you also want to make sure that this resistance is sufficiently low. But that one, at least in a common source, it's easy to get it very low because you can put white metal traces over here between source and bullock. The gate, you can try to keep it as low as possible. Yeah, that's it. Try to keep it as low as possible. The drain, actually, we don't care too much about the drain. If there is a lot of parasitic resistance at the drain, well, remember that the drain source resistance is maybe 100 ohms to 500 ohms. So if that parasitic drain resistance is maybe 10 ohms, who cares, right? So that's the benefit. You can tolerate much more parasitic resistance at the drain than at the gate and at the source.